Hello, good afternoon, everyone. My name is Lieutenant Colonel Michael McDaniel, or Mick McDaniel, representing Mr. Dreen, the Department of the Air Force Chief Data Officer. I'd like to welcome everyone to the November Innovation Connect, hosted by the Department of the Air Force Chief Data Office. So for folks that were able to join us a few weeks ago, we were lucky enough to have the CIO of the U.S. Army Corps of Engineers and then the Director of DIU Boston present a couple of briefs and presentations for the group. So today we are lucky to have the Director of SOFWERX, Ms. Leslie Babich, as well as Dr. James Stockton from the Chief Data Office team to discuss, to do some presentations as well. So the purpose of Innovation Connect is really just to make those connections, exchange those ideas, give a forum for those out there in the innovation space, a platform to kind of present and then seek feedback and share ideas as folks come up with new ways of doing things. And that's really the purpose of why we're here today. So just a few housekeeping rules. I think these were on the last slide, but if you could list the questions, so everyone have your video and microphone on mute, video on off. And if you have a question during the presentation, recommend you just add it to the chat on the WebEx feature. And then Ms. King will be moderating, and we'll have a presentation section, and then we'll go through with questions after that. So first, I'd like to introduce our first speaker, Ms. Leslie Babich. She is leading the team of innovators down at SOFWERX in Tampa, Florida, supporting U.S. Special Operations Command. So she brings a wealth of operational experience to that position. 20 plus years where she's an MC1, where she served as an MC-130 pilot, was a squadron commander, as well as a commander of Joint Special Operations Air Component as well. So brings a ton of operational experience, and we're very pleased to have her here today. So Ms. Babich, thank you very much and welcome, and thank you for joining us.
Hey, Mick, thank you very much for that kind introduction. I'm hoping everybody can see and hear me at this point.
We can see you and hear you.
All right, yes, great. Well, thank you for all the participants today. I see we even have someone from the United States Space Force, so congratulations on the stand-up of that organization. Awesome accomplishment. So without any further ado, I will start my presentation. So I'll share, and then just let me know when you guys can see the presentation, and we'll move forward. All right, I think I've got it up and ready to go. So SOFWERX, it's been in existence for it's approaching 6 years. I've been the director for exactly 1 month, so I'm pretty new here, but already floored by the capability that we can provide to SOCOM. So SOFWERX was established under a Title 15 partnership intermediary agreement with SOCOM and DefenseWERX. There are several other hubs that have been established under DefenseWERX with different organizations in government. And you'll see It WERX is a partnership with the Army Civil Defense or Civil Engineering Command. CIFIC is a partner with Army Cyber Command, and we've got a couple other partnerships as well. We are a 501c nonprofit, and we're funded entirely by SOCOM. So we have an operating budget that funds the salary, rent, et cetera, but all of our events initiatives that we hold here at SOFWERX are free. Our corporate headquarters is located in Niceville, Florida, and again, they hold PS for multiple other organizations. And the good thing about that is we can do collaboration across the hubs because they each have their area of specificity and focus. So, you know, CIFIC is more cyber. ERDIX is obviously civil engineering, et cetera. So why was SOFWERX established? Number one, we started looking at innovation trends and realized that innovation in government was starting to go more slowly than the commercial world, and that most of the innovation base was kind of intimidated with working with the government. They also found the government to be very slow. And so the solution to that problem was SOFWERX. And so our goal is to create the bridge between government and non-traditional businesses and to bring the smart minds together to solve warfighter problems and challenges, and really identify those best-of-breed capabilities that we can put in the hands of the warfighter. And we want to do that quickly. Because we're non-FAR based, we work with a Big Tent philosophy, and you can see all the other organizations that we work with to find solutions to warfighter problems. That includes Special Operations Command. We have multiple entities within the command, interagency partners who we work with overseas and here in the United States. We work with industry partners and fellows, federally funded research and development, laboratories, academia, internships, and we also work with hackers. They are ethical hackers, and really they are able to give really no kidding good feedback to our commanders and our warfighters in terms of internet security, et cetera, and security of our systems. So on to the next slide, and I don't have the chat up right now. So if you guys have any questions before I flip to the next slide, please don't hesitate to ask. So this is how it works here at SOFWERX, really our process. And what we do is we accept, the warfighters will identify challenges out on the battlefield or in the headquarters with the systems, processes, equipment that they have that don't enable them to fully execute the mission as they would like. So we want to try and streamline that and make them more effective and give them that asymmetric advantage. And challenges can come through several different avenues. They're all coming from the warfighter, but it could either go through the components, and by that I mean AFSOC, MARSOC, USASOC, and Naval Special Warfare Command. It can come through the Theater Special Operations Commands, which are theater-based, and they're really the more of the warfighting component out in the field. And also it can come through the headquarters and the joint staff. But the big thing is we want to make sure that with any challenge, what does short-term and long-term success look like for them? We want to make sure that we're treating the symptom or treating the disease and not the symptom of the problem. And also we want to make sure that there's an acquisition strategy that is tied to that, so that it's enough of a priority for the command or that unit that they want to put resources behind finding that solution. There's a couple, so what we'll do, once we understand fully the problem, we can sit down with the warfighter or whoever identified the challenge and determine the correct mechanism to apply to best find the solution. And you can see below the various different mechanisms that we have used in the past. We've got really good templates for all of these, but obviously they're not all exactly the same as an end result when they come out, because we really want to tailor it to the problem at hand. And we'll walk you guys through a couple of these projects here in just a moment. And they come through several different avenues. So once we've really identified the problem, we're going to release that opportunity to the ecosystem. And it's an email blast. And we reserve our email blast for those problems that we want folks help us to solve. We don't send out newsletters. We don't send out any other kind of emails, because we want to make sure that this really catches their attention and that this is something that they can help us solve. So once we get the ecosystem blast out, vendors and small businesses and whoever wants to participate has 30 days to put a submission in after release. And so this is, again, really us trying to accelerate to get that solution into the hands of the warfighter. So we hold tight to these timelines. And then US SOCOM, so we're a neutral party. I see us as kind of like a matchmaking application where we're discovering in the ecosystem all of the potential solutions, and we put that out there to our government partners, and then they make the decision on what solutions that they want to pursue. So they have 10 days to make that down select, and then we will reach back out to those entities that were down selected, and we'll do a more in detail, face-to-face, one-on-one government with the event, and we'll host that here or wherever it needs to be hosted to ensure that they really understand the requirements of the government, and if there's any specifics that maybe they fully didn't understand. Then they'll do another assessment really with that business, And at the end of the day, we'll get to that dashed line, and there's some outcomes that can occur from this. So before we get to the outcomes, I do want to walk you through a couple of projects that we had recently here at SOFWERX. So I'm going to play a video, and I will talk you through it as it goes. All right, so this first one is it's called the Silent Tactical Energy Enhanced Dismount. And basically, this is one of the challenges that came to us through Army Futures Command, not necessarily within our enterprise here in SOCOM. But 3 years ago, our National Mission Forces had identified a need for a supplemental carrying system, and they collaborated with Hendricks Motorsports to come up with this an initial prototype solution. And then 3 years later, Army Futures Command kind of discovered the capability, and they really wanted to develop it further to see if it was appropriate to solve some of their problems. So Army Futures Command brought this challenge to SOCOM, and we collaborated further with them to develop and further test this. We call it the STEED capability. So we have a USOC LNO who worked with the Asymmetric Warfare Group representative, and we started to plan a combat evaluation for this vehicle. And really the goal was to validate the efficacy of the capability and its potential utility, again, for USOC in the U.S. Army. So a lot of times SOCOM will develop a capability, and then we'll share it with the service in hopes that they'll adopt it for their use as well. So this is one of those cases at the end of the day. But back in May, SOFWERX, Hendricks Motorsports, the Army Physics Lab, and Army Futures Command, and Warfighter representatives met up in Virginia to test the STEED. And basically we tested 3 concepts of operation in different environments. And that was in a rural, an urban, and a subterranean environment. And we had 3 different CONOPs, and U.S. Army personnel executed those CONOPs both with the help of this vehicle and without the help. And so if they didn't have the vehicle, they had to have all their PPE on, and they had to carry it in themselves. And what they did, they tracked the biometrics of each of the soldiers. They monitored all of that to provide a comparative analysis of the human performance in both scenarios. And at the end of the day, they provided a combat evaluation report to the end user and the technical point of contact for the Army. And the Army is definitely interested in this technology, and I believe they've already made some purchases. And actually, the 7th Special Forces Group has made some purchases as well. The testing was very beneficial for this final version of the STEED that you see. I mean, it goes up and down stairs, all different kinds of terrain. It can be used for equipment, and that's very important in teams of 12 or even smaller. Sometimes we're sending in teams of 4. They've got a lot of equipment to bring in, and this really enables them to bring that equipment in and still maintain their physical health throughout the mission. And so, because of the combat evaluation, the warfighters were able to provide their feedback directly to Hendricks Motorsports, and they were able to make those slight modifications from the initial prototypes and really get this into the hands of the warfighter very quickly. So does anybody have any questions on this capability or how it went through the process? This is very quickly a combat evaluation because a prototype had already been developed, and we just wanted to further assess to see how it could support Army solutions in 7th Group. All right. And so you've got a second example here, and this is the Blast Exposure Monitoring System collaboration event. This came through the more traditional pathway through the SOCOM enterprise, and basically we're trying to identify an objective way to monitor blast exposure in the environment that our operators are often exposed to. Right now, we were relying on self-reporting and subjective metrics like how are you feeling, rather than really having objective data to monitor the soldier and get real feedback that could then be sent to the medical community and used to track and figure out how to better treat and protect the soldiers during these events. So basically, we identified the challenge in early 2020. We did a collaboration event, which is where you'll have government representatives sit down with the warfighter to make sure they fully understand what the problem is and what they're trying to solve. And from that, they down selected from all of the folks that attended the collaboration event to 7 companies, and they moved them on to the assessment event. So for the assessment event, it's really a one-on-one with government, and they sit down and talk through the capability to see how they can modify an existing capability or create something new based on what they have now. But at the end of the day, we had 2 OTAs that came out of the event, and it will be a system that is attached to the warfighter to monitor vitals and where a blast, when a blast occurs, what was the impact of the blast, et cetera. This feedback can be provided to the operator's ATAC, which is an Android system that they carry in the field for situational awareness. It can also be provided back to their command if they're sitting in an operations center, et cetera, and eventually provided back up to the medical folks. That's another example that we had, and this happened very quickly. Most of our events, assessment events, happen, the average time frame is 60 to 90 days from when we put out the ecosystem blast to when we get down to the assessment. And at the end of the day, the assessment event, we can actually purchase the technology. I'll get back to this. So we can actually purchase the technology from whichever vendor was down selected to. We can put the technology, we can do a collaborative project order if we feel that the technology readiness level or the technology needs to be developed further before it gets put into the hands of the warfighter. And that's what happened with the BMO. The other impacts, it's important to monitor, if our process is working and what the impact of that is to the warfighter. So we break down the impacts really into 5 different areas. And the first is a knowledge transfer, and we look at it like a bullseye. And so the outer ring is any kind of new knowledge or technology that we weren't tracking before. And I think it might not be used right away, but it's really important too, I think, to share, you don't know what you don't know. So if we can put some knowledge into some folks' hands and they're looking at future problems, they can circle back around and go, yeah, I remember this technology. This is potentially a solution to a problem that we're having right now. The next step is validation. That's the next ring in the bullseye. And it's not necessarily validation of the technology, but a validation of the application of that technology to solve a problem, and to see if we can identify a coalition of the willing that wants to pursue that further down the road to solve some problems. The next one is a collaborative project order, and I talked on that briefly, but it's the ability to take some technology that might be at a technology readiness level of 2 or 3, and we set up a business-to-business agreement between SOFWERX and the company that has the technology to further develop that, to get it to that next TRL level and get it closer, to the warfighter. And then the fourth one that we have here is consignment. And so between consignment and transition, we're really talking about scale of the solution. So if it's we only need like 100 of them, and it's a commercially available off-the-shelf technology that just needs to be slightly modified, we can do a consignment and purchase that. And the money is provided by SOCOM, but we can enable that consignment and get that over to the warfighter. And finally, if it's a larger scale or something we want to integrate into an existing program of record or create a new program of record, that's what we're talking about with transitions. So as of today, those are the impacts that we've had using this SOFWERX capability. Does anybody have any questions on this slide?
There are some questions. We usually hold the questions until after the presentation, but do you want me to go ahead and read them now?
If it's relevant to this slide, I'm happy to answer it now.
I think there were some on the previous
okay.
video that you just did.
I'll have to figure out. Let me pull up my chat again.
No, so the first one was, how did SOFWERX discover that Hendrix was the right company to partner with?
Okay, so that occurred when the National Mission Forces were looking for a solution to this problem initially. So a lot of times during the Eco Blast, and we will do a lot of targeted market research too when we have a problem that we're trying to solve. We've got a lot of tools for that, and so we will actually go research companies that have technology similar to what we're looking for and reach out to them specifically to see if they're interested in helping. So it's targeted market research in this case.
Okay. The next question was, what are the rough specs with speed, sound, and signature in use? For the speed? I believe so, yes.
We can send that to you guys if you're interested. And it's actually a commercially available product right now. And so there's vendors that are selling this to the commercial folks as well. So I believe it's already online and available. But we'll get that information to you.
Okay, thank you. And then the last one in the chat right now, does SOFWERX coordinate their efforts, research, and solution with the Defense Innovation Unit or DIU?
Some of these are coordinated. It depends on where the challenge came from and the specific warfighter, but I know we have coordinated and worked with them on items in the past. So DefenseWERX, again, is an umbrella, and we've got multiple hubs. And DefenseWERX has a chief technology officer. His name's Brad Chedister. So he does a lot of coordination across the hubs and between other innovation organizations to ensure that, we're kind of tracking if there's similar efforts going on in different innovation units so that we're not stovepiped and that we're trying to leverage each other's efforts and we're not repeating research or something that's already been done in the past. So Brad is very helpful in doing that for us.
Okay, thank you. That's all of the questions right now. If you wanted to continue at the end, we'll let people unmute their phones and ask questions at the Q&A at the end of your presentation as well.
Okay, we'll head to the next slide. All right, so a couple of lessons learned over the past years, and this slide is broken into two different parts. And first is the lessons learned, and then we'll talk about the chart. But really for us, maintaining momentum, I know that people have limited bandwidth and focus. This is really tied to the amount of time that we want to spend on a project, and we really want to spend 60 to 90 days and be very focused effort and get it, potential solutions into the hand of the warfighter. Also, pivot quickly when it doesn't work. If we can fail fast and we know it's not working, we don't want to continue down that path, wasting time and resources on an idea that's just not going to work for us or for SOCOM. The third one, you can't force adoption. I think, we've got some great technology out there. Sometimes a requirement doesn't actually exist for it. So we can't push that solution on the government if it's not going to solve a problem that they have right now. But it's good that they know that this technology exists in case it can apply to a future problem. And second, everybody, it's reality. We're resource constrained. So there's some great ideas out there, but they might not be feasible in terms of cost. So sometimes it's the best idea, best capability that we can afford at the time. Also, finding products for your customers and not customers for your products. There's a lot of good technology out there, and if there's not a requirement for it, we will share the information with them, but we're certainly not going to force a product on our customer. And then owning the numbers and not doing innovation theater, that's really tied to having an acquisition strategy at the very beginning. Because it's really important for us to know that if we're sending out an ecosystem blast to our partners in our ecosystem, that there is potential at the end of this exercise and these evaluation events for buying the technology right away, for their developing, et cetera. We're not just showing, the vendors aren't just showing up and not getting any specific feedback or opportunity for a partnership with the government. And executing fiercely and demanding excellence, again, that's really holding to the timeline and paying attention to the detail of our process. And finally, being a team of committed stress reducers, we can reduce the burden, I think, on already overburdened staff, both in acquisition and in the teams and the warfighters. They're focusing on their current problems. And if we can reduce that stress and do this discovery and engagement piece for them and figure out what technology is out there to support their problems, then that's what we want to do. Over to the chart. So really, this is the law of theory of diffusion. And so we're trying to focus on all the folks to the left of that orange bar. And those are the innovators and early adopters. And that's who we're trying to reach out to in terms of technology in our ecosystem. There's so much out there that we're not tracking, especially the warfighter. And if we can focus on that, what we're trying to do. So a lot of programs of record will do incremental improvements to a platform. And I'll just take a 130, for example, right? We've had the 130 since the 1960s. And we've done incremental improvements to that platform to meet the new challenges in terms of how we're going to fight wars and what we need that platform to do. And so if we can, as an organization, SOFWERX, look and see what technology is out there to even like potentially boost that incremental improvement beyond what they knew was out there, and kind of it slows down or lessens the number of cycles that you have to go through to achieve an improvement that will last for more than just a couple years. And that goes for all the different programs of record. I think a lot too, we can inform requirements and decisions that are already, somebody's got an idea of a solution that they want, but we can help inform them of what that solution might be, or refine their idea on what's really in the realm of the possible for that. So that's where we're looking at, and that'll lead us really to our next slide. So for us, our focus on technology, we try to break it up into 3 groups, and it's 40% on incremental improvements, 30% on adjacent, which is commercial solutions that already exist, but with slight tweaks, we can get them to apply to a government problem. And then the transformational technology, which is really that cutting edge technology that, these folks might be working out in their garage. They've never really done business before with the government, and to reach out to those folks because they have some great ideas in technology. They just haven't worked with government before. So we're looking at the 40-30-30 split. And our Tech Tuesday is a forum that we have each Tuesday, and folks will submit through our website, and we'll take a look at the technology and see. We think it's really, truly transformational, and they have the opportunity to present to SOCOM and other interested users from the government. You can see a list of folks that have attended our Tech Tuesdays in the past. But it's a really good opportunity to look at that transformational technology. And again, it might not apply to a solution that we have right now, but if they have that information and further down the road, if they have a problem, it might apply. Additionally, even if it doesn't make it to the briefing stage, we'll shoot it out to folks that might be interested in it. If it's, more adjacent or an incremental improvement, we'll share that with our partners. We don't want to cut off the flow of information coming in. We're just trying to bid it at this point to do the transformational look. And then a couple of things. So how is SOFWERX different? We are non-FAR based business, so we can do business-to-business agreements with smaller businesses. There's no qualification for coming to SOFWERX. Sometimes with small business, innovation research, there's qualifications before you're approved for that program. We can do business-to-business with any organization that has the technology that we would like to pursue to solve a warfighter problem. Right now, 84% of our submissions come from our ecosystem, and 16% come from SAM.gov. And SAM.gov, those are the folks that have done traditional business with the government over the past several years. So we're really trying to bring in more folks and more solutions to the warfighter. And again, we're a neutral party. And the cool thing about that is, the government's not really allowed to say, hey, there's a company that we're working with here and this company over here that we're also doing business with. They should work together and maybe they can come up with a newer solution, but we can do that at SOFWERX. We can also negotiate lower rates to do some of these assessments and evaluations than the government can. So in a sense, it's a cost savings for them. And then everybody knows, I think at least it's intimidating for some to get onto a base and to go into SOCOM headquarters and to try and do business with government. And so this is really a low barrier access point. We're in Ybor City. It's very easy to get into our building. It's a great collaboration space. And so it just creates a lot more enabling environment, I think, for people to start work with the government. And then why SOFWERX? You know, it's quick wins for the warfighter. If we can get something to them in 60 to 90 days without going through and you know, a lot of our events and collaboration and assessment events, they create that competition, you know, that is required for a lot of awards. And so we're doing that through our assessment events, and they can actually, you know, purchase things at the end of the day, at the end of the assessment event, and get it to the warfighter. So it's quick, it gets it to their hands, and oftentimes it's pretty low cost. For fail fast and cost and risk avoidance, these are, you know, if we've got a program of record, they really want to pursue this technology. It allows us to look at this technology and say, is it going to work, yes or no, without going through a whole lot of bureaucracy. And if it's not going to work, you know, they can turn it off and they can look to the next potential solution. So we're doing a lot of cost and risk avoidance in terms of resources and time, going down that path where if you hadn't done this in the first place, 2 years down the road, you figure out this technology is not really what you're looking for. It's not going to work. It's tough to turn back at that point for a program of record. And I think I've talked about it before, but this information can help inform and refine requirements that are already existing and that they're trying to create for a new program of record as well. And then again, we talked about it. We can do additional contracting mechanisms beyond just FAR-based contracts. And really, this is our last slide, but how to get involved with SOFWERX. SOFWERX.org is our ecosystem. We've got a lot of folks reaching out to us. They have got this kind of technology. Are you guys interested? So we really want to direct folks to SOFWERX.org to see what potential focus areas we have out there, potential events coming up. You know, we've recently done one for austere 3D printing, welding. We're doing a tech sprint for automated analytics. There's a lot going on, and this is the way to find out what's coming up. Again, if there's transformational technology, we recommend the Tech Tuesday forum, also on our website. And you can also participate in an event as a SME. You know, if you would like to be a government observer for one of our events, or as a SME, you can do that as well. And that's pretty much it. So if you guys have any questions for the briefing, please let us know. And again, I don't have the chat up, so.
Okay, yeah, no problem. So yeah, if anybody does have questions and you're on the phone, you may have to hit *6, or you're welcome to unmute yourself. I'm going to just ask a few that we got here. What is the SOFWERX team, and how many projects do you take on every year?
So the SOFWERX team itself decides. We have 22 permanent staff. We also have interns, primarily from USF, University of Southern Florida. That's how the program was started up. Started out with about 3 to 4, but at this point we have up to 30 throughout the year. We've also expanded that reach really across the country. We've had interns from Auburn University, Eastern Kentucky, University of California, Berkeley, University of Tampa, Florida Institute of Technology, et cetera. So we really get a lot of expertise from the interns. You know, they're studying the newest technologies. They've got great ideas. And the other benefit of that is we're developing that next generation of innovators and agile thinkers, and really exposing them to how to, you know, work with the government. And I think there was a second part to the question. I'm not sure I answered it.
Yeah, how many projects do you take on every year?
We'll take on as many as SOCOM wants to do. It's really, it depends on their budget and how much they want to spend, but there really isn't any limit, I think, to the amount of projects that we can do for them. And again, it takes the burden off of them to discover the technology, do the collaboration. And so our goal is, you know, to hand them a package at the end of the event and say, now it's your turn to decide, you know, how you want to go forward with your acquisition strategy.
Mm-hmm. Okay, I'm going to pause real quick and see if anybody on the line wanted to ask a question. Okay, none here. I have a couple more here. So you mentioned the Tech Talk Tuesdays. Are there any other Tech Talks or hackathons coming up that interested parties could participate in?
I don't think we have any hackathons coming up right away, but you can always sign up on softworx.org and you will get an email blast when we have events coming up. I think there's 2 events on there right now.
And there is a tech talk coming up pending for December that will be released here in the next week or so. Okay. And let's see, I've got one. I'm getting some on Teams here too. So could you give a quick overview of SOFWERX STEM?
Sure. We've done collaboration events locally and nationwide. Christina, you might be able to talk better to the details of each of the events. But
yeah, hi everybody. My name is Christina Hurd. I'm actually one of the STEM leads here, so I appreciate that question. We work with elementary, middle, high school, as well as college. College is mainly through our internship programs, but we do run collaboration events where students will come to the facility, learn more about what it takes to be an innovation. We've done multiple career fairs. We're actually participating in a couple engineering club projects this week, as well as Great American Teach-In next week. One of our greatest loves is robotics, so we do fund VEX Robotics and have a couple engineers that are SOFWERX employees that actually help lead those teams, and then teams will actually come back. We've hosted the robotic kickoff event the last 3 years in a row, and so those teams will actually come back to SOFWERX, and it's called a robot bag and tag. We'll give them feedback on their robots, how to enhance them, but some pretty incredible capabilities. We've been able to expand a lot recently. We're thankful to USOCOM, who gives us a dedicated budget for all things STEM every year. Fantastic, thank you. We have another one in the chat here. They said, interesting point about lowering the barrier to entry regarding office space. How has that changed with the pandemic?
Yeah, so what we've done is created a lot more virtual events. This is a pretty big collaboration facility, so we're open for business. We've got plenty of space for social distancing and, wearing masks. But, if a lot of folks are not able to travel, we've probably transitioned to more 90% virtual events versus face-to-face.
Okay, I think that is all the questions in the chat right now. Did anybody on the line have a question? Okay, and if you're on the phone and you wanted to ask a question, you may have to hit *6. All right, well, Ms. Hurd, thank you very much, Ms. Babich and Ms. Hurd. We appreciate you participating today, and you're welcome to stick around for the next presenter.
All right, thanks again for the opportunity. Really appreciate it.
Absolutely. Okay, next up we have Dr. James Stockton. Dr. Stockton is a data scientist with Altamira Technologies, and he is currently also working as the lead data scientist for the Department of the Air Force's Chief Data Office, one of our own. He has been with the Chief Data Office since its inception in 2017 and has led many varied analytics efforts across the Department of the Air Force enterprise. He has worked previously as a data scientist supporting clients in the intelligence community and private industry. Dr. Stockton received his bachelor's degree in mathematics and physics from Drury University and his PhD in astronomy from New Mexico State University. Dr. Stockton, thank you for joining today. The floor is yours.
Hi, good afternoon, everybody. I suppose first, let's see if we can share some slides. So yeah, as Kelly mentioned, I've been a data scientist supporting the Chief Data Office for about 3 years. And have done a bunch of different projects all over the enterprise, lots of different interesting things. The one I was asked to talk about today is specifically around a project we did with LCMC supporting the CBM Plus program. And it's centered on actually decoding flight data recorder information from KC-135s to make them usable basically for predictive maintenance. So the typical Bluff slide here I'll talk over. the general idea was simply that the raw data that was available from the flight data recorders off of the aircraft was kind of owned by the Air Force and available for whatever use they might want, but it's in a compressed binary format that's not readily readable. Basically, the vendor processing those for them provided a subset of the data in a useful format, but when asked for the full suite of available sensors in a time series CSV kind of top to bottom format, that wasn't something that the U.S. had an organic capability to produce. And so there were third-party solutions, software licensing, those sorts of things to try to generate that. Advance the slide. There we go. So yeah, as I was saying, LCMC's CBM Plus program this is 18 months ago or so, was at the point where they had done a lot of great work looking at expected lifetime curves for individual components coming off of aircraft. So if you've got a lot of widgets, particular lot number, and you know that on average they last X flight hours, you can start to make intelligent decisions about preemptively replacing parts. So if you've already spent tons of maintainer hours to tear apart an engine to fix a problem or something that broke, but you're also really sure that this other part's probably going to break in the next 5 or 6 flight hours, go ahead and replace it now while you've got the engine torn apart to save yourself the time of tearing the engine back apart in a few more flight hours. That kind of trade space. So they had done a lot of great work with that, and they were looking to kind of take a next step on predictive maintenance and start monitoring the behavior of sensors over time. So with a longitudinal data set of, say, oil pressure, for instance, if you're at typical operating parameters on a 135 and your oil pressure is generally here with some noise in it, and then all of a sudden you start to see oil pressure creeping up on the same aircraft, on the same engine over time, that's the kind of early warning that they were hoping to get. Of course, the first step to being able to do that kind of predictive maintenance is to actually have the sensor data, and that's what we were looking to help them out with. So we kind of came across this project about this time last year, a little over a year ago, I guess, and there was a maintenance sprint in A4 where they were looking at ways to kind of maintenance of the future sort of thing. And we went and participated in a few of the initial presentations to kind of get up to speed with what they were looking to do, provide some data science support from the Chief Data Office. Ultimately, they needed some data architecture kind of support, but while we were there, we did connect with LCMC's EZP guys and were able to kind of hash out a project that we thought we could help them out with. So ultimately, the project came down to, if you have a black box, essentially, here's a data set of binary compressed formatted flight data recorder data. It's ones and zeros. It's essentially gibberish. There's no clear pattern. It's not in a typical format. What can you do with it? Can we crack that open and decipher it and generate a kind of Air Force owned, organically produced flight data decoder so that we can actually look at all that second by second, moment by moment sensor data and start doing some predictive maintenance with it. So kind of breaking that problem down. And in fact, I want to pause here. I know that the typical format is to maybe field questions at the end. We're going to dive down into some details about the actual method and the solution we came up with to crack open the file structure. And so it maybe is a little esoteric in parts. And if anybody has any particular questions, put them in the chat. And Callie, please feel free to interrupt me. And it might make more sense for everybody's understanding to kind of answer them as we go, if there's any kind of particular technical question.
Will do.
Okay. So to kind of frame the problem, in a typical a file that's saved on your computer, it's almost always saved in memory addresses that are 8-bit chunks, 1 byte. that's pretty much the standard encoding scheme for memory addressing on SSD hard drives, spinning platters, RAM, whatever it is. You're typically talking about memory being stored 8 bits at a time, so 1 byte. If there are any coders out there, basically even something that really only needs 1 byte, so if you've got like a true-false kind of variable, or sorry, 1 bit, if a true-false kind of variable really only needs 1 bit, it's either on or off. But as far as the operating system of your computer is concerned, it tends to store things in this 8-bit chunk, so 1 byte. Even though you might only be using 1 bit in that byte, the memory is still going to use all 8 bits because that's just the way the memory addressing works typically. So one of the problems we had with this file is that going into it, it's a complete black box. We don't know what it is really formatted like, except we were pretty sure that it was not going to respect this kind of 8 bits at a time structure. The reason for that is simply they were looking to squeeze as much information as possible into as small a memory footprint as they could manage, which means you might have a sensor that is a toggle switch. And so it really does just need 1 bit of information to record that, the state of that switch. It's either on or off. So a 1 or a 0. Some other sensor on the aircraft might have, 6-position slider bar, so you need 3 bits to record that, and so on. You might have a very high precision oil pressure sensor that needs 16 bits in order to record the very precise number, 2.xxxx bars. Some very many decimal places down. You might need a very high precision measurement, which takes a relatively large number of bits to encode. And all of these are going to be kind of just packed in right next to each other in order to fit as much information as possible in as small a memory footprint as possible. So everything I just said is kind of represented by this toy diagram down here at the bottom. So you can see on the bottom kind of row, you've got this alternating blue and gray structure. That's kind of representing the general idea with recording information on a typical system. So you've got 8 bits, this first section of blue, and no matter how many bits you need to record your information, it's going to store it in that 8. And if you need more than 8, it'll store it in an adjacent extra 8. So you've got this kind of on-off either-or memory footprint. The row above that with multiple colors is kind of representing what the flight data recorder is doing. So the different sensors that are on board record information at different rates. So you might have sensors that are recording once a second, twice a second, 4, 8 times a second. My memory serves me. It's 8 hertz was the fastest sensor that we were dealing with. And those readings just come in as they come in. And so they get stacked up. And so you end up with kind of a jumble of information. It's a little bit of a mess. And if you naively try to read that information in 8 bits at a time, 1 byte at a time, as is typical, you're going to either split the information from one sensor into multiple pieces, or you might compile the information from 2 different sensors into one value, and you're going to get the wrong information, essentially. So fundamentally, we had to understand the structure of these sensor values and how they were arranged in this one-dimensional bit stream that was coming in from the compressed binary file.
Okay, and we do have a question.
Sure.
How does the Air Force label or annotate the source data so it can be ingestible into an ML AI development effort?
That's a huge question. So in this particular instance, these are raw flight data recorder files. It's an RDF format, raw data format. We've actually, subsequent to this project, and actually currently we're working with some people at Tinker to pull in a SISMIS data. I think I have that acronym correct. It's basically all of this raw data. We're working to get that uploaded into the Vault data platform and start decoding some of the KC-135 files that we have. So essentially, we're in the process of trying to kind of register that data and make it more usable for analysts. But as far as the Air Force doing that in general, it's kind of more of a database by database answer. I don't know that I have an enterprise-wide answer for you. Any others, Callie?
Yeah, one just came in. So it's a follow-up to that one. The reason he asked is that his company does secure data annotation specifically for USG. We have cleared staff and SMEs to annotate it. We are working with NGA and others in DoD and would like help from the Department of the Air Force.
Yeah, I think maybe a follow-up conversation there probably most fruitful.
We'll put you two in touch. Another question. Will Dr. Stockton's briefs be available? Yes. Oh, so everyone just as a follow-up to that, all the briefs will be available, and I will touch on that at the end of the presentation.
Okay. Great. So the fundamental task we had was to kind of open up this black box. It's a compressed binary file. What's in there? And can we open it up and rearrange the bits from this one-dimensional bit stream into clusters of bits that go to the same sensor? That's really what we need to be able to do, is to identify which bits in which location belong to which sensor as a function of time, and rearrange all those, convert them to integers, convert it to instrument value, and then write all that back out in a more user-friendly kind of CSV time series data format, where we've got time going down with rows, and then every column is a sensor. And so it's kind of getting from that, compressed binary file format to that useful output structure. That was the fundamental kind of goal of this use case. So going into this, we were relatively blind as far as the underlying structure. And additionally, we were not flight data recorder experts in any stretch of the imagination, but it was something that we felt we could tackle, and it basically was kind of a cryptography problem at some level. And so we tried to attack it a couple of different ways, because fundamentally we knew that there were going to be periodicities in the data set, right? So some of these sensors were recording at 4 or 8 times a second, and sensor values that repeat that frequently may be changing, but they're not changing wildly. And so you should see similar measurements, 8 times a second for a 30-minute flight. That means you're going to see lots and lots of the same measurement kind of sprinkled through. And if you think of the accumulation of all of those sensors, so there were 152 sensors, if I remember correctly. But if we simplify the problem and just think of, say, like 4 sensors, and they record once a second, what you're going to get is, sensor 1, sensor 2, sensor 3, sensor 4, all of the bits associated with their measurements stacked together, and then you're going to get sensor 1 again, and then sensor 2 again, and sensor 3 again. And so you're going to get these kind of cycle lengths, where one cycle is all of the sensors have recorded at least one measurement. It gets a little complicated when you think about all the different sensors recording at different rates, but what we were looking for was that fundamental cycle length. How many bits do we have to go out so that we have gotten each sensor at least once? And so the first kind of tool that we attacked that problem with was fast Fourier transform, discrete Fourier transform, kind of bread and butter signals analysis method. It's a little bit complicated in this case because of the fact that we're dealing with binary data. It's literally a 0 or a 1. Usually, Fourier transform is applied to a continuous time value, the discrete Fourier transform discretizes that. But on the y-axis, your response value is still continuous. You're measuring something that's smoothly changing between two extremes. Since we were dealing with binary data, it's literally a 0 or a 1. That actually introduced some artifacts in the output of the Fourier transform that were confusing at first. But then we built some data just some synthetic data that we knew exactly what was going on, applied the same method to it, and basically saw some ringing effects where you would get power at different frequencies. You get outputs that basically said, there's some periodicity at this frequency, there's some periodicity at this frequency. and there'd be a fundamental frequency and then some interesting kind of integer divisions. So at half and a third and a fourth, you would see a curious kind of behavior there. But once we understood that behavior, we were able to pull out some bit lengths based on this Fourier transform of the bit stream, where we were pretty sure that there were basically 8 or 10 lengths in bits that had some power at different frequencies. And so we knew that we were kind of on the right track. We were kind of understanding that these pieces were piled up. But we wanted to double check that essentially. And so if we look on the right-hand side here, this is just a completely different way to attack the same problem. So one of the basic insight we had here was, if you reach out, say 100 bits, and you assume that it takes 100 bits to record all of our sensors, and then you kind of chop that there, and you chop off the next 100 bits, and so on, and you stack all these up to make a two-dimensional array, you may have picked the right number, or you might not have. And if you did pick the right number, then somewhere in that array, one of those columns is going to be all of the sensor values for one sensor. And so the idea was simply that if you were to check one of these and you picked the right number and you converted one of the columns to the right sensor, then if you looked at the sensor value from one time step to the next, there would be a small difference. Because even if you're accelerating or in the middle of a dive and you're measuring altitude or something, the altitude is changing pretty quickly. But if it's an 8 hertz sensor, the actual value from 1/8 of a second to the next 1/8 of a second is still going to be relatively similar, even if you're in a steep dive and you're measuring altitude. And so if we were to measure those differences and then look at the standard deviation of those differences, that's actually a single number that gives us information about, did we pick the right width for the array? Did we find the right cycle length? And then did we find the right column, essentially? And so this piece of the plot here in the back basically is a diagram showing about 160 million different possible combinations of start column and cycle length. So basically we just brute forced the one-dimensional bit stream and calculated this standard deviation of the first derivative. And where that standard deviation was low, we would expect to be near the correct answer as far as the cycle length position. And so you can see, if I filter this plot in the back and only look at the low standard deviations, that's what the one in the foreground is. And you can see there's some interesting behavior in the plot. Essentially, we've got quite a few piled up around a cycle length of 3,000 bits. And then there's something around 8,100 bits, around 12,000, around 16,000. And there's a little bit of a repeating pattern. And you can't quite tell from the plot, but if you go look at the actual values, they're exactly multiples of each other. So it's, I can't remember exactly, but it's 8,120, I think, and then 12,240 and 16,480, however that works out. But essentially the cycle length here around 8,000 is exactly half of the cycle length here that's around 16,000, which is what you would expect if you were getting something that was the correct length, and then you got something that was twice the correct length. You'd still expect to get some decent measures. So basically, these were two completely independent mathematical methods to try and kind of pluck apart the bit stream and understand the cycle length. How many bits do we need to go before we chop the bit stream and say that's time step number 1, and then roll everything under and find time step number 2. So that was a whole lot of description. And then basically, I'm hoping that this short video kind of explains it as well. So each one of these gray boxes you can kind of imagine as a sensor that's recording some value. It might be a 12-bit sensor, or it might be a 2-bit sensor, 8 bits, doesn't matter. Sensors are just recording their information and piling up time step by time step. And so if there's a particular sensor that you're looking for, represented here in red, what you would like to be able to do is take this one-dimensional bit stream and find this cycle length, the fundamental unit, and chop the data there and start piling it up into a kind of time series row by row. But if you choose the wrong cycle length, you're essentially jumbling all the data. So when you look at one column, you now have the data from multiple sensors mixed together in one column, which is not helpful. So if you then choose a slightly longer cycle length, demonstrated here, you can see that we're getting closer. And then if you were to pick the correct cycle length, you're going to end up having all of the bits associated with a particular sensor will line up vertically in your data table. And so this is what we were looking for, and what I was trying to describe on the previous slide is that you can basically brute force this width search and hopefully come across a cycle length that makes sense. The problem is it's not quite as simple because we have those multiple sensors recording at different hertz, at different rates. And so you're actually looking for multiple cycles that are all kind of interlaced together. So it's not a perfectly clean result, kind of like this video shows, but that's the idea. So what we were able to do is, based on the output from the Fourier transform method, we had a small handful of candidate cycle lengths, and then based on the kind of standard deviation of the first derivative method, we don't really have a good name for it. We just kind of invented it at some level. And that one output a small handful of potential cycle lengths as well, and they largely overlapped. So that really narrowed the search space from, instead of some hundreds of millions of bits, we were able to then cut it down to 4 or 5 potential lengths that we were interested in chopping it, and then that made the search space manageable. So once we got to this point, we were able to then go and search for individual sensors. So if we assume a certain set of bits belongs to a particular sensor, we can just convert that to its physical value. So we did have some specification information for the sensors on board, and we were able to tell that this oil pressure sensor takes 12 bits to encode a numerical value between this range and this range. And so from that information, we're able to write a little bit of code that takes an arbitrary bit stream, converts that to what it would be if it were an oil pressure sensor. And we could apply that across the data set and basically go find some of these actual values, kind of needles in this haystack of random bits. But that method is really only tractable after you found these cycle lengths that make it a little more plausible to brute force that part. As we built that up, we then basically started to understand some small pieces of the bit stream that actually served as tags. So as we went through and found some of the sensors, we also found that there were markers basically in the bit stream. If you knew they were there, then they're extremely helpful. But since we were coming into this, blind, it's a proprietary, binary encoding structure. We were basically searching for those signposts and had to find them by playing all these kind of math tricks to find some sensors, and then eventually start to identify some of these signposts. And like many problems like this, there was a large amount of time kind of banging your head on the keyboard, digging at it, not making much progress, and then eventually you kind of you start a snowball where everything starts to make sense. And so it was around this point where we really started to crack this open and identify essentially frames. So clusters of sensors that recorded at the same rate would be recorded as a unit, and there'd be a small, it was 32 bits that would lead that set of measurements. And those 32 bits were themselves broken into pieces that identified what sensors were coming next, basically. And once we realized that, we were able to say, when we see this tag, we know that this many bits following it goes to this set of sensors. And then we would read past that many bits, read the next tag, and so on. So that basically let us build a piece of code that would parse the bit stream, the one-dimensional bit stream coming out of the raw flight data recorder, into buckets of like sensors. So basically all the sensors that recorded 1 hertz, all the sensors that recorded 2 hertz, 4 hertz, 8 hertz, and so on. Once we were able to kind of crack it open and understand some of these signposts, we were able to build some code that does this parsing. So this is kind of a one-dimensional bit stream reading into our decoder. Represented here is our little yellow box. And you can see it's reading these tags, and now that we understand what's there, we're able to parse the appropriate number of bits off into each bucket, and now we're getting really close to that kind of format that we actually wanted, where we've got time running down row by row, and then across the top, we've got bits that are associated with particular sensors all aligned in the same column. So essentially, there was a bunch of upfront work to understand the bit stream, but then once we kind of cracked the code, it was a relatively simple matter to write some code that very quickly parses this out into the appropriate buckets. And then once each one of these groups of sensors is broken out into apples and oranges, you're able to then go across each column and start the task of figuring out which column goes to which sensor, but you have the advantage of knowing that all of the bits in a particular column go to the same sensor, and so we're able to identify which goes to which. So ultimately, this was kind of the underlying structure of the FDR files. So inside the raw file itself were kind of two pieces. There were what we ended up calling kind of session data. It's the sensor data for a sortie. And then there's also kind of file data, which is giving you information about the suite of sensors that are on that FDR. So basically what's on board, and then here's all the data. So understanding that first level of structure, let us break it apart. And then there's another file kind of buried in there called the ASC database file, aircraft specific configuration file that detailed which sensors were available. And then this is basically a flow chart kind of that decoding process I was describing. So the aircraft specific configuration file that's listed there basically looked like what you see on the left, pulling that out of the bit stream, and then it's a kind of classic mid-90s ASCII formatted file that's not especially user-friendly. So one of the tasks we did was to just reformat that into kind of the tabular format you see on the right, much easier to use in our coding for the actual decoder. So this is basically telling you specific information about a sensor. So for instance, oil pressure number 2, there's some precision information, tells you this function V is basically most of these sensors are voltmeters. So there's a voltage coming down a wire, and it's recording a voltage. So you're taking bits into an integer, which then you use that integer to plug into a function that converts that integer voltage into an actual sensor value, a physical value. And there's some other information over here, upper and lower limits on the sensors and so on. So all of the stuff we talked about up to this point was basically understanding the file structure so we could parse all of the bits that went to a particular sensor into one bucket. And now that we've got them assorted by time, we need to actually convert them from their binary format into a physical unit so that's actually useful. And so that's what this information basically was. So we had some issues there, basically, as you can imagine. And there were a lot of parts and pieces. We went back to the KC-135 program office and got some documentation that helped us kind of understand those binary to integer to voltage to physical unit conversions and how we could streamline that. And then ultimately found out that one detail there, maybe a little in the weeds, but basically the integers in the binary bit stream were actually stored in 2's complement, which is typical. There were some reasons that we thought initially it was sign and magnitude format, which kind of sent us down a wrong turn for a little bit, but we did eventually get back on track. And so then the other kind of major piece of understanding how to actually do this was slowly kind of parsing the aircraft-specific configuration file that came off of the FDR and understanding what it was trying to tell us. So eventually, you can see there's some information that identifies these frames I was talking about, where sensors of different recording rate were grouped together, and then given an ID for a particular sensor, you can come look up the specs for it, as far as, what's its ID number, how many bits, upper and lower limit, the sign method that it's stored with, and then this voltage to physical conversion function. And so slowly piecing together how to walk the bits of information in this file to make a good conversion of the bits once you had parsed them correctly was another kind of issue. And of course, I've kind of described this process relatively linearly, but of course it all happened kind of together with fits and starts of understanding at different pieces, and then slowly they were kind of connected together and let us kind of crack this open. So then the last step we had, once we thought we could make a good conversion, was to kind of check our work. So we went back to the use case sponsor, and they had a handful basically of flights, I think it was 5 if I remember correctly, where they had the sensor values for us to compare against. So going through kind of our converted values and looking at the output we had for one of those flights, there were 135 sensors that had numerical values, so 12.222 or whatever it may be. Out of those 135 sensors, 127 of those sensors agreed on every time step from our conversion and the validation that came from a third-party vendor software. And so we dug a little harder on those handful of sensors that didn't match, and discovered that they were always exactly differing by 1 unit of precision. So, if it was a sensor that recorded to the first decimal place, every time step where our value differed from the third-party vendor's value, it differed by 0.1. If it was a 3 decimal place, then it was in the 3rd decimal place, right? So it was always the least significant digit in the measurement where we differed. And then, interestingly, if you look on the kind of plots on the right here, the difference was always in the same direction. So we were calculating those basically by the comparison value minus our value, and that was always positive, which basically told us they were always rounding down. So what we basically discovered was they were doing a floor division in their conversion, which led to cases where they might have something that would be equivalent to 12.6, and they would round that down to 12.0, whereas we were rounding it to 13. 13 in that example, I guess. But basically, we were rounding up and down as necessary based on a 0.5 split, which is generally typical. And it looked like the differences we were seeing with our comparison values were because they were doing a floor division in their conversion. So ultimately, we were satisfied that we were converting sensibly and passed the decoder back to our use case sponsors at EZB. They did some of their own testing, basically, so they had an existing cloud environment where they were doing some of their predictive maintenance work and their expected lifetime curve work that they had been running with for a while. Basically, they got it up and running in their AWS environment, started decoding, and seemed to be working great. So they basically told us that it was decoding successfully, and they trusted the outcomes. So that was as of April, I think, roughly of this year. In the meantime, we've gone back to Tinker and the Sysmus database and gotten a bulk delivery of a bunch of these flight data recorder files, both from the KC-135 and other platforms, and we're in the process of uploading those into the Vault data platform for use. We've got a small subset of the KC-135 data that we're trying to move into an accessible part of the Vault right now. It's roughly 8,500 flights, August 2019 to November, or I said that backwards. I think November 2019 to August 2020. The older files are in a slightly different format, not the decoder part, but it's literally just stored as an Oracle database dump file. We're working on reconstituting that so we can output the actual RDFs and then decode those as well. This is kind of working with the AI Accelerator guys and Lincoln Labs to make these available for them and other analysts in the Vault Data Platform. So, questions?
Okay, we do have one on Teams. How do you handle missing data or prevent data leakage, and what imputation techniques do you use?
So we're not really imputing any values or handling missing data in the typical kind of data science sense, where you might have an existing tabular data set with a record that's missing a value for some sensor. This is literally a bit-to-bit conversion. So in the case of a sensor, in the case of bad data, basically, you're going to see in our output downstream of our decoding, an analyst would basically say, why is this oil pressure sensor recording, 1 million pascals? That's too high. That kind of question is outside the scope of the decoder, because we're literally just saying, these are the bits recorded by the flight data recorder. This is what they convert into in physical units, and doing that kind of parsing structure to get all of the information for one sensor into one column. And so that imputation step is kind of a downstream analysis piece. It's not directly applicable here, because we're literally just taking the raw binary data and turning it into raw sensor data in physical units. We're not looking to make any assumptions or obscure anything. It's literally just, this is what the flight data recorder had on board.
Okay, and what's next for the CBM Plus project?
So the CBM Plus team at LCMC is kind of off and running with their predictive maintenance work. So, given access to these time series, high frequency measurements, they're able to do, the typical predictive maintenance work of monitor, each tail number over time, anomaly detection, that kind of thing in a given sensor. And given historical data, there's also, and I'm taking a step deeper into their process that I don't know about. So I guess to answer your question directly, they've got access to this time series data, and they were moving out with their predictive maintenance efforts, period. I presume that entails, going back and decoding the historical data that they have available and looking at the maintenance histories of different tails. And so there's a whole rich data set there that they could work with, where you're looking for, maintenance action X happened on this date. Let's go back and look at the relevant sensor history for the some amount of time in the past and see if there's any clear anomalies in the sensors that would provide predictive capacity for that necessary maintenance action. That's the kind of thing that you'd be looking to do with these data.
Okay, let's see. What organization sponsors CBM Plus, and where is it hosted?
So CBM Plus is a program run out of LCMC, Lifecycle Maintenance Command, and I think it may have moved to EZP. We're not directly involved with the predictive maintenance work that they're doing, short of enabling them by providing this decoder. I don't know that there's not like a CBM Plus portal that has data available that I'm aware of. That's kind of why we were reaching back out to the Asysmos data and trying to do some of the decoding in the Vault data platform, so that we would be able to provide that data for other analysts. But as far as contact information, if you send me a note, basically, or Callie, if you can pass on contact information from me, we can put you in contact with the people at the CBM Plus program.
Sure, absolutely. And just so everybody is reminded, you are welcome to come off mute if you wanted to ask a question. If you are on the phone, you can use *6 to come off mute. Otherwise, you would just hit the little microphone button at the bottom of your screen there. And I'll pause and see if anybody has any questions. Okay, none heard. So thank you very much, Dr. Stockton.
Yeah, thanks. It was a little in the weeds, but hopefully were interesting.
Yeah. Yeah, so this concludes today's Innovation Connect. Due to holidays and scheduling, we are going to take December off, but we will restart the program January 14th of 2021. For the 2021 Innovation Connect series, it'll be held on the second Thursday of every month, and we are currently booking all of our 2021 speakers. So if you have a topic that you'd like to present or you'd like to hear more about something here, you can please reach out to myself, Callie King. Videos of this event and other Innovation Connects are going to be published on the Department of the Air Force CDO YouTube page. We encourage everyone to follow us on Twitter and LinkedIn to keep up with the information and upcoming events. Thank you all for taking the time to attend today's program. We look forward to seeing you again in January, and that closes out today's Innovation Connect.